Welcome, MCT4C, day 46. This is first day on dividing polynomials. I'm calling it 5.8, although we're using the Addison-Wesley textbook more and more in this section because our book actually doesn't do this stuff at all, and it's good, clean fun, so we are going to do it. The 3-minute review is a little bit long, maybe more like a 13-minute review, but I've got my answers up here. And I'll just go through them real quick. It's a cubic, so it starts low and ends high, and the x-intercepts are -3 and +4, and there's a bounce at +4, so it looks something like that. And notice that I put another point on there for scale. Similarly on this one, with the cubic there's one factor and 3 more make a degree 4, so this is going to be a quartic. It's an M or a W. Since the leading coefficient is negative, it starts low and ends low, slashes at 0, and then slides at 5. And it looks like it's going to bounce, but then slides through and goes down. Point in there for scale. The third one, well, it's not in factored form, but we learned all of those factor techniques last day, so let's put them to good use. I took out a common factor of x, left me with a difference of squares inside, x minus 3, x plus 3, bada bing, bada boom. We got 3 roots, a point for scale, and this one looks like it's odd, right? It looks like one of these ones that is a double flip or a point symmetry. You know, a point over here ends up going through, and then there's a point over here. This is actually an odd function. And notice the formula has got all odd degree letters on it. One that I did want to show you is this expanding, and this is just hard expanding, so let's get practice here. And I'm going to multiply the last 2 brackets first. Doesn't really matter, but multiply everything times everything. Collect like terms inside that bracket before we start multiplying. Multiply everything times everything. X times this, that, and 2 times that, and that. And I'm going to do it sort of a way that'll help us find the like terms better. X times x squared is x cubed. X times 3x is 3x squared. X times -4 is -4x. 2 times x squared, and I'm going to write it down here. Instead of writing it over here, I'm going to write it down here, and then I'm going to add this way, you see. 2 times 3x is 6x, 2 times -8, and then I'm going to add that way, and I get altogether x cubed plus 5x plus 2x minus 8. And today, what we're going to want to do is take that and end up with that, or at least we're going to start that process. It'll be a process that we're on for a couple of days. So let's get into it. Dividing polynomials, and again, we're in the Addison-Wesley textbook, not in our normal textbook. Simplify polynomial expressions by factoring using various strategies. We have been doing this for several days, and we'll do a couple more days of this. To graph this or that, we need to factor. But how? Well, that one wasn't so bad. It was a common factor in different squares, but how do we factor this? I could try grouping. It doesn't work. It's not quadratic form. What's frustrating here is this is the answer to the 3-minute review question. That's this one. So we know it can be done, right? This is that x plus 2, x minus 1, and x plus 4. The question is how would we ever get that? Well, it has to do with dividing. Factoring is like dividing. So we know that if we had this, and you've been able to go this way for several years now, since grade 10 probably, you had some questions where you had to multiply 3 brackets and get that. That's expanding, which is multiplying, right? Multiplying everything by everything. But this is what we really want to do. I want to be able to give you a function, and then you be able to write it in factored form so we could graph it, right? This is factoring. And it's got to do with dividing. The only thing is we don't know how to divide polynomials. We barely probably remember how to divide numbers. And so we're actually going to get going on dividing polynomials by dividing numbers, long dividing numbers. So I got 27, and I'm going to do long division into 4298. And here we go. How do we do this? This is going to take us a little while because it's a pain. Well, how many times does 27 go into 4? Well, it doesn't even make any sense. I'm going to go to 2 digits. How many times does 27 go into 42? Well, it goes in once. And so what I'm going to do is go back and forth between colors here so I can explain my steps, okay? So that one was, I thought 42 divided by 27 is 1. How many times did 27 go into 42? Well, it was 1 time. Put my orange marker back here. Okay, so what's the next step? Well, then we go 1 times 27 and write that here, right? 1 times 27 and write that there. That was 1 times 27, wasn't it? Well, what's the next step? Well, I subtract, right? I would subtract here. 12 subtract 7 is, doesn't go, I'd have to carry. 12 subtract 7 is 5, 3 subtract 2 is 1. So what step was that? Well, I subtract. Oops. If you don't remember these steps, that's okay. And remember, we had to end up with a number that was less than 27. Otherwise, we would have goofed up, and we would have had to go back and fix this and change it to 2 or 3 or something else. The next step then was bring down the 9, right? That was the next step, bring down the 9. And then the nice thing is this whole process just sort of kept going, right? We just continued that process. So, well, how many times does 27 go into 159? After you sort of mess around with it a bit, you'll find out that it's 5 times. And then I multiply. 3 times 7 is 35. And then 3, that's 13. 13. And then I subtract. This is the same steps, right? So what did I do there? I went 5 times 27 gave me the 135, and then the 24 was subtracting. And I knew that I did a good job because this answer is less than that one. It's all good. Now I'm going to bring down the 8. How many times does 27 go into 248? A whole bunch. Multiply 9 times 27. 63, carry the 6, 18 and 6 is 24, and I subtract. And now that I'm out of numbers, I see that there's a remainder. So is 27 a factor? I would say in big fat letters, no. In fact, 4,298 is 27 times 159 and then a remainder of 5. And this is a setup here. This was the divisor. This is the quotient. And that's the remainder. If that remainder was 0, then we'd have a factor. And of course, this is what we want when we're using polynomials. Say, well, why are we doing this? I haven't done this since grade 5. Why are we doing it? Well, the process for dividing polynomials feels and looks almost exactly like this, okay? So let's try one. Here we go. We're asked to divide this into that? Well, here we go. And by the way, this is weird. It looks weird. It's weird math. It's a lot of steps, a lot of places to make a mistake. Be patient. It's a little bit of fun, too. It's a type of math you take it home and show it, you show somebody at home, mom, dad, grandma, grandpa, or whoever, what you've been doing. And they say, you're so smart. It looks so impressive when we get this done right. All right, so what was the first step? The first step was to take whatever we're dividing by and figure out how much it goes into the first little bit, right? Over here, it was how many times does 27 go into 42? It's kind of hard to think about how many times an expression goes into another expression, but essentially what we want to do is we want to pick a value so that when I multiply, because I know the next step is multiply, that when I subtract, the expression will be smaller. I don't want to have anything here. This has got to be blank. This has got to be 0. So that's the whole strategy, is I want to pick a value so that when I multiply, I'm going to go here, x plus 3 times something, and that when I subtract, the x cubed is gone. And in that same way, essentially, I wanted to pick something that when I multiplied and subtract, that number was smaller in magnitude than the 27. So what is it? I want to think ahead and multiply this by something so that this ends up being x cubed. So when then I subtract, this will be gone. That's the plan. Well, what would I need to multiply by so that happens? X squared. X squared times x is x cubed. X squared times 3, I got to do that one still. And then I subtract. Now I should have this in a different color so it all looks, the blue is the work and the red is the explanation. So where did the x squared come from? Think. What do we multiply by so that when we subtract, the x cubed disappears. That's what we're thinking. Disappears. And x cubed will do or x squared will do the trick. And of course, the second part, multiplying by the 3, x squared times the 3, well, that's like a tag along. And now I have to subtract, right? I subtract. Be careful now. -2 subtract 3 is -5x. And that's kind of like this subtract right here, right? Well, what was the next step? The next step was to bring down the 9. Well, I'm not going to bring down a 9. What I'm going to do is I am going to bring down the 14. Well, 14x. Oops. I missed some squares there. Excuse me. Well, that's the next step. Next step. Bring down the 14x. And now we have another go. It's just like in long dividing, the process repeats. So what am I going to multiply by? What am I going to choose to multiply by so that when I multiply this, I end up with no -5x. So this has to be -5x squared so that when I subtract, it's gone. So thinking backwards, what does this have to be? Well, it's going to be -5x, isn't it? Because -5x times x plus 3 will give me the -5x squared there. So when I subtract, that term will be gone. All right, well, what's the rest? -5x times +3 is -15x. And then I subtract, watch your signs. 14x subtract -15x is 29x, and this is going to get a bit nasty. And of course, -5x squared, that's gone, just like I planned. Now I'm going to bring down the 1 and go again. Well, what number am I going to multiply by so that when I subtract, this part's gone. 29, isn't it? 29 times x, and then 29 times 3. Well, 29 times 3 is, what's that? 87. And then I subtract. And I subtract. So negative 1 subtract is negative 88. I just noticed that I didn't put the steps in earlier. I want to go back and write in all the steps, so at least for this first one you'll see. How did this, where did this line come from? This line came from subtracting, right? And I'm going to clean that up so it reads better as well. That was x squared times x plus 3 that allowed us to get that. And this is just like the long division. Okay? And we're going to try another one. This is, it looks weird, but it's impressive, isn't it? Okay. Notice that at the end of this, how we sum this up is to write what's called a division statement. So this division statement is the thing that I started with is equal to the x plus 3 times the quotient plus the remainder. And notice what that means. It means x plus 3 doesn't divide evenly into this thing. That whenever there's a remainder, it doesn't divide. So that's the divisor. That's what we're dividing by. Quotient is the answer to a divide question, and there's the remainder. Okay, I think we got a couple more examples, so I'm going to stop this first part of the video and pick it up in part 2.